to, there was my title slide, never mind. We'll carry on, and we'll carry on and start with the 4th of June, just 3 weeks ago. On the left there, you can see a picture of one of the sky surveys that NASA funds, the Asteroid Terrestrial Last Alert Survey, or ATLAS. Twin telescopes operating in Hawaii in a project run by John Tonry out there. And on the 4th of June this year, 3 weeks ago, as I said, it was scanning the sky every clear night as it's designed to, and it spotted a small moving dot of light. Now, on the right-hand side, you can see those images, and helpfully outlined in a red cross, not on the original images. They're not that easy to spot, everyone. But on the right-hand side, you hopefully can see a small moving dot of light. This did not match anything in the current catalogues of asteroids or comets. It did not match where we expected satellites to be. And so it was reported to the worldwide community as a potentially another new object. And it was given the project name A1075TQ. And so, on the 4th of June, we had a detection of a potential new object from one observatory. 48 hours later, we had observations from 15 different observatories of that new object, ranging from England and Romania, here in Europe, over to Australia, Japan, and even South America, Brazil. And it's by putting those observations, those careful, precise measurements of the position of this object in the night sky from these various locations from Earth, that the trajectory or the orbit of the object could be calculated initially, and it was realized, yes, this was a new object. It's actually a potentially hazardous object, 2008 LK, and from those observations, the orbit can be seen here on the screen. So we have the Sun in the center, the inner planets, Mercury, Venus, Earth, and Mars, and here you can see where the Earth was with 2018 LK, as it's now known, just passing outside. Now, from this initial orbit, we can already say that although potentially this object can pass closer to the planet Earth than our moon, it probably won't hit us in the next 100 years. To know that more accurately, we need more observations. We'll need to do particularly the sophisticated orbit determination that Ed was talking about earlier. But it looks like, at least for this one object, then this is not our problem, but it may well be our grandchildren's problem or our great-grandchildren's problem. And when we detect something like this, however, we know an approximate size, but only approximately. And this is one of our problems with survey telescopes here on Earth at the moment. We only know of the apparent brightness of the object, how much sunlight it reflects. And we don't know what kind of object that is, because we know of two broad classes of object in our solar system. On the left, we can see a near-Earth asteroid. In fact, this is Itokawa, imaged during the rendezvous by the first Hayabusa mission a few years ago now. And these objects are predominantly rocky. On the right, we have Comet 67P, imaged by the tremendously successful ESA Rosetta mission a couple of years ago. These objects are particularly icy. Now, normally when those icy objects, those comets, are near the sun, as you can see, the sun's heat evaporates or sublimates the subsurface ices. They stream away into space, along with entrained small particles of dust, and they form the atmospheres and the tails that we see. And so sometimes when you take an image of an object, it's quite clear it's a comet. Here's an image taken last week from Atlas of a particular comet that was actually discovered 2 years previously, 2016 M1. And one could see very clearly the beautiful tail stretching off to the left. And by the way, this is a nice example, this sequence of images, of why it's good that we have to use sophisticated computer software to locate new objects in the sky, because as a human being, I'm immediately distracted by this beautiful comet travelling against the background stars, and I can completely miss the small asteroid travelling above it in the sky. So you might think it's disappointing not to look through the telescope, but let's be honest about it, the only way to do this is with sophisticated computer software and coding, and that's what happens every clear night with these survey telescopes. But we still don't know for that small object above there. We don't know its inherent properties. All we know is how much sunlight it's reflecting. We don't know if it's a small, bright, inherently bright asteroid or a larger, dark but inert comet nucleus. And there's one survey, however, that can do this at the moment operating. This is the NEOWISE survey. That's the repurposed infrared survey telescope that NASA launched several years ago now. And the difference between infrared telescopes in space and optical telescopes on the ground is that when you detect something in the infrared, you're not detecting it generally by the light it reflects, but you're detecting the object by the heat radiation, the thermal radiation it emits. And that immediately allows you to see not only where it is, but also determine its size. So it's an incredibly important way to find these things, although, as I said, we only have one such survey in orbit at the moment. And although the survey's been going for a few years now and it's detected many large objects, recently one member of the team, Joe Mesiero, has gone back over the data and tried to find the smaller objects that were missed in the first pass through the NEOWISE survey, but were detected by ground-based telescopes. So this is a plot where we've got size on the bottom, and we're going in kilometers from, again, it's logarithmic scale, we're going from 10 meters through 100 meters to a kilometer across. And here we've got the albedo, which is what astronomers call the reflectivity. If you're at the top, you reflect all the light that hits you. Pretty much you're a mirror. If you go down to the bottom, you're darker than a piece of coal, which, funnily enough, is about the same inherent brightness as a comet nucleus. And one can see in red now this really nice study of these smaller objects, including objects of the size that Mark was talking about, the objects that can create these potentially damaging, even fatal airbursts on the ground on Earth. And one can see clearly that they span a range of inherent brightnesses as when we detect them, when we see them in space. And that's important for us because it tells us that we've got to be very careful when we find small objects that we don't assume we know too much about their size. If we don't measure their size in another way, we don't really know the threat from that object to a great degree of accuracy, and it's something that does need to be addressed in the future. Now, apart from such studies there's another way you can determine the intrinsic property of these asteroids, and that's through splitting the light up into a spectrum, so to basically see how much light is reflected as a function of wavelength. So here what I've done is I've plotted the reflectivity, roughly or relatively how much light is reflected from these objects, as a function of wavelength of light, going from blue and green and red optical wavelengths here, but stretching way out into the near-infrared region of the spectrum. And you can see that different types of asteroid, different types of rock reflect light differently. And not only do they reflect relative amounts of light differently, we know from previous studies that they reflect absolute amounts of light differently. So if you look at the top right, you can see a relatively fresh silicate or rocky meteorite found here on Earth, and you can see that's reflecting quite a bit of light. They reflect 20–25% of the light that hits them. If we look below that on the bottom right, you can see a carbonaceous meteorite that comes from a very carbon-rich asteroid, and they reflect very much less light. And again, that shows us that we have to be very careful when we assign diameters to the objects that we find out there. And in fact, Rusty here is holding, it's going to pass around a meteorite. Now this you've got to be careful about because this has come through the Earth's atmosphere at about 10 miles a second, 17 kilometers, or about 15 kilometers a second. So you've got a very rich fusion crust on the surface, but it's also a very dense metallic a piece of dense metallic asteroid, very rich in iron and nickel. And that is the kind of thing that we also really want to be worried about, because you really don't want that hitting you on the head at 15 kilometers a second. So, now, surveying the asteroids out there, particularly the small near-Earth asteroids, is something that's very important to do as well, to know the nature of the beast that we're particularly concerned about. And there's been a recent study of that by Dorin Prunariu here in Europe. And 5 minutes, I'll march on very quickly now, showing that many of the sub-kilometer asteroids are rich in a mineral called olivine. And this is important because it shows us that these were once part of a much larger object. We know that when you form large asteroids in the early days of the solar system, they'll be structured rather similar to the Earth. You'll have a crust, a mantle, and an iron-rich core, similar to the fragment that's being passed around now. And we know these olivine-rich asteroids, which there seems to be an unexpected number of these in the small near-Earth asteroid population are out there. Now, what about the entire population as a whole? Ed has spoken again previously about creating these maps, but it'd be nice to know what are the boundaries of the maps, and we do that by looking at the numbers of objects that are detected and trying to work backwards to figure out what is the population of near-Earth objects out there in the space, that most of which will not hit us, but some of which can. And so this is work done by Michael Granvik, where he's taken a simulated asteroid belt up here on the top left and then integrated it in the computer over 100 million years using gravity and various other forces to figure out where those asteroids go and which objects come out into near-Earth space. And the important thing is, first of all, on the top right, that gives us, as I said, a potential boundary for the maps that Ed wants to produce, because it tells us where the majority of the near-Earth objects should be. It also tells us, importantly, where they come from. And Michael Granvik and his team have shown that most of the Earth impactors come from the inner asteroid belt rather than further out. But the best thing about this is that it gives us some confidence that although we might not know where all those asteroids are that could potentially hit us, we know how many there are that we've still got to find. And that's shown on the bottom right there, where there are various size distributions or brightness distributions found by investigators. And they all pretty much agree, down to about 100 meters diameter or so. So we're pretty clear, we know how many there are out there to find, and as we've heard, we've still got a lot to find so far. Below 100 meters, when we get down to Tunguska size and Chelyabinsk size, there's still some disagreement, and clearly that's an avenue of work that needs to be concentrated on in the future. Now, when these surveys take place, you occasionally find other interesting objects, and let's get right up to the present day, because in the last 48 hours or even 24 hours, we've had some wonderful results in this field. First of all, if we go back, though, to October last year, the Pan-STARRS survey telescope, also in Hawaii, saw this little streak of light in 4 of its images on the 19th of October. And subsequent follow-up over the next few days determined that this object was not gravitationally bound to our sun. In other words, this was the first alien object definitely detected from Earth traveling through our solar system. We didn't see it on the way in. It was too close to the sun in the sky, or too faint to see on the way in. But as you can see on the right-hand side, it dived down from above our solar system, or for the people from Australia and New Zealand, it came up from above. Did almost a right-angle turn around the sun, but that was purely due to gravity and the strong gravity passing so close to the sun, and then headed out. And we had about a week of observations. On the left-hand side, there's an image that I took with my team from the telescopes in the Canary Islands. On the right, we have an artist's impression of what it potentially looked like. And at this stage, we thought we still didn't know, even if it was an asteroid or a comet. Now, we got observations using both the telescopes in the Canary Islands and Chile on the left-hand side, again, showing how this object reflected light, and we couldn't tell, because it looks like it could be a comet, and in fact we did calculations to show it could still have ice inside, but it would also possibly be similar to what we call D or dark type asteroids out towards Jupiter. But then yesterday it was announced that a team led by Marco Micheli at the European Space Agency's SSA project had done a beautiful analysis of both the data and the positions reported both from Earth-based telescopes and the Hubble Space Telescope. And they found that if they just use gravity plus all the other much weaker forces, such as the thermal forces that, again, Ed mentioned earlier, they couldn't quite get the orbit to work. But if they included one additional thing, outgassing, weak outgassing from buried subsurface ice that we suspected could be there, then everything worked. So what we have now is a much clearer picture of Oumuamua. What we have is not the first interstellar asteroid, but the first interstellar comet seen passing through our solar system. And we almost lost that in the news yesterday, that tremendous finding, because, of course, yesterday the Hayabusa 2 mission also arrived at its home position 20 kilometers from near-Earth asteroid Ryugu. Now, it's a fantastic mission. It arrived there, as we said yesterday. It's going to be there for about a year and a half until it departs at the end of next year. It's going to deploy landers. It's going to get a sample and bring that sample of this asteroid back to Earth at the end of 2020. The one thing that people have commented on is the strange shape of this object. 800 meters across, and it looks almost like a child's spinning top. Well, actually, it matches what we already know of many other near-Earth asteroids imaged by the JPL asteroid radar teams who use the Arecibo and Goldstone antennas, where we see this very clearly. And we understand it, even, because we know that asteroids can be spun up and slowed down simply due to the action of thermal effects. And if you have a rubble pile asteroid, as that happens, you see you can develop very easily the equatorial ridge and even form moons, small moons, about near-Earth asteroids. And indeed, we know about 15% of near-Earth asteroids have moons, which is another tag for Ed's upcoming map of near-Earth space. So I just want to leave you with the impression that there's a huge amount of work going on at the moment in science of asteroids. There are new results coming out every year, almost every month. And if we just go over what we now know, we've already got 18,444 near-Earth objects on the books as of yesterday. I'm not quite as quick as Mark as picking up stuff. We've got NEOWISE and other telescopes measuring size and compositions. We know how many near-Earth objects there are out there, even if we haven't found them all, down to about 100 meters or so. We're getting our first detections of asteroids and comets, not just from our solar system, but from other solar systems. And we have a year and a half, not only of Hayabusa 2 at Ryugu, but later on this year, the NASA OSIRIS-REx mission arriving at asteroid Bennu. It's going to be a great year or more in the future for asteroid science. Thank you.
Thank you, Alan. So let's take about 7 minutes or so for questions for Alan.
I've blinded them all with science.
We have one here.
I was wondering, what instruments or resources would you like to see to detect more asteroids if you could choose investment in that asteroid detection?
Okay, well, in case people didn't hear that at the back, the question was if I could use any or afford to buy or purchase or design or build any instrument to enhance asteroid detection, what would I build? And I think this has been known in the community for quite a while now. What we need is a powerful infrared space telescope that is interior to the Earth's orbit. And because there, first of all, we not only get the detections of the objects, but we also do know the size. So I think that's crucial. At the same time, if we have it interior to the Earth's orbit, we're not always looking outwards, out into the solar system as we are with our ground-based telescopes right now. If we're inside the Earth's orbit, we see the stuff that's actually around the Earth at any one time, and that gives us a much better completeness. Now, there are other ways to do it. You can do this optically as well, if one wants to use optical telescopes. I still favour, personally, the infrared telescopes because we get the size as well as the object, but one could certainly foresee systems, and many have been proposed, where one uses optical data because you can actually go down to smaller sizes with optical facilities still, I believe.
Did you have another answer?
Well, I had another question.
Go ahead.
I didn't really think about this till you showed the right angle trajectory of Oumuamua as it got to its perihelion. And something with that aspect ratio, if it's true, should have experienced extreme tidal forces, right? Has anybody, I mean, I'm sure somebody's calculated that, but do you know what that is?
No, I don't. I mean,
It's definitely not a rubble pile.
It's definitely not a rubble pile, although maybe it started off as a rubble pile and maybe it consolidated itself in the millions or even billions of years it's been traveling out there in interstellar space before it got to us. But yeah, one thing that I also didn't mention was that when it did this right-angle turn around the sun, effectively due to gravity, what we now see is that it's not spinning simply as well. This object is tumbling through space, in that it's rotating through about more than one axis in itself. And it could be that I'm not sure anyone has done that calculation yet, but it could be that close passage past our sun may have enhanced that tumbling. But what we don't think it started because the tumbling is so strong. It looks like it was set tumbling before or during its ejection from its home planetary system. And as I just mentioned, we don't know where that home planetary system was, and we don't know where it came from. In fact, it could have been there up to 10 billion years. We don't know yet, and we may never know. But we're waiting for the next one.
Other questions? Yes.
In speaking about infrared telescopes and optical telescopes, I was wondering if there are other technologies, maybe even in theory, that we could use maybe later to spot asteroids or other celestial bodies that might be more effective, because this seems like a quite limiting factor, isn't it? To use IR and optical.
So the question is, are there any other technologies apart from IR and optical to use for detecting asteroids? Well, we're kind of constrained by a lot of the physics there. So, for example, at the moment we detect asteroids by reflected sunlight mostly, and the sun emits most of its light in the optical region. That's why our eyes have evolved that way, and we have other experts in the audience that could explain that much better than I have. So if we're dealing with reflected light, we could certainly want to stick with the optical telescopes. Similarly with the infrared, when we're looking for near-Earth asteroids, you want to use telescopes in the near infrared, maybe a little bit longer wavelength than we're using at the moment to detect them further out. But we know, again, from the physics that anything at a particular temperature emits most of its thermal radiation at particular wavelengths. And so the near infrared region is pretty good for us as well there. Now, there are other technologies you might consider, for example, radar. And radar is certainly used to allow tracking, give incredibly precise tracking of near-Earth objects when they're close enough to the Earth, and also, of course, resolve them and get their size. But the problem there is that the radar falls off as 1 over distance to the power 4. Which is an incredibly strong discriminant. It means you can really only detect objects relatively close to you. So it's hard to see whether or not how you do better than working in the optical and the infrared. One thing, however, again, to go back to is that perhaps what we want to think about is not just keeping our telescopes all at Earth. If we put them out there and get their detections out there, out amongst that swarm, not just in one location, then you can detect these objects at a much faster rate.
Yes, sir.
Your preferred
That's a good question. I think for the initial problem of trying to find all these objects down to 140 meters across, or even 100 meters across if you want to go lower than that, it doesn't need to be at the Lagrange point, a stable point between the Earth and the Sun, so it keeps track with us. Although there, you do minimize your problems with data transmission, because you always know where the object is and the distance doesn't vary. But it would be good to have some kind of system whereby you are actually closer in. Closer into the Sun, because we know there's a population of objects that spend most of their time within the Earth's orbit, and we're very insensitive to those at the moment, and we would even be insensitive to those at the L1 Lagrangian point. So getting close into the Sun than that would be preferable. But there are practical aspects in terms of particularly getting the data back from those space observatories. That means that maybe L1 is a better option in the long term, just in terms of getting those findings back.
And I'm going to cut it off there, and thank you very much, Alan. That last question, most of these guys are going to disappear to a press conference after this part of the event. Excuse me a minute. However, Dorin and I will be around, and we can talk a little bit more about that particular question. Now, I'm going to shift gears a little bit here. What you have been hearing up until this point, with the exception of part of Mark's talk, have been technical aspects of near-Earth asteroid issues, and in particular planetary defense. That is what you might call early warning and prediction, that kind of thing. But there's a whole section of things we haven't talked about, and that is, what do you do about it? And that comes under the category of deflection. Now, I don't know where the asteroid has made it now. Oh, it's back here, okay. Well, let me say one thing right off the bat. That's not going to hit us. That does hit the Earth once in a great while, and the interesting thing is that those are the ones we find. The rest of them are like stones. They're much lighter, but they're much harder to find because they look like rocks or stones, okay? So the ones that actually, there's only less than 5% of the near-Earth objects that are made of iron nickel, as that one is. So don't let that get in your head as to what an asteroid is like. Asteroid is like a very lightweight rock in general. Now, nevertheless, because they're moving so fast, forget that. Velocity squared is the energy. The mass is less important than the velocity. So the energy is there no matter. Now let me say a word about deflection to introduce the last speaker, Dorin Prunariu, because deflection introduces an element that is non-technical, which is geopolitical. And when you look at the overall probability of somebody in the future getting killed by an asteroid that hit the Earth, it's because, in all likelihood, we knew all the stuff about it technically, but geopolitically we screwed up. We didn't make a decision to act. That's the most likely reason in the future that somebody's going to get killed by an asteroid. Okay? So I'm going to introduce that by explaining why geopolitics enters into this game. So visualize an Earth out there in front of you. You're an asteroid, you're headed toward that Earth, okay? Now, if you're going to hit the Earth, if you have any possibility of hitting the Earth, the plane of your orbit has to intersect the Earth. If the plane of your orbit doesn't intersect the Earth, you can't hit it, all right? So if you picture a line all the way across the Earth, that's the intersection of the plane that you're in. That line goes all the way across the Earth, and if you're going to hit the Earth, you're going to hit somewhere on that line. Now, for a moment, imagine it's right in the middle. Line all the way across, intersection, you're actually going to hit in the middle. Okay, so that's the impact point. A deflection, by necessity, says that you're going to move that intersection point off the Earth along that line, either, let me say, to the right or to the left. You can make the line vertical also. But anyway, you're going to deflect the asteroid, and that impact point is going to either be dragged along the line one direction or the other direction, or it's going to pop along the line if you're doing an impact type of deflection. But one way or the other, you got to move it that way or that way. People live along that line. The people over here say, do it that way. The people over here say, do it that way. People, national leaders are being elected over here too. Okay? Who says, okay, even though it's going to end up off the Earth, there is a slight possibility something will go wrong, and it's just going to move from here to here on top of my country. Okay? Who pays to do that? These guys or those guys or everybody? How about people off the line? They're not even at risk. Should they pay to move it off the line? Those are all geopolitical decisions that have to be made in the event an impact is predicted. And the result of when we realized that in our early work with deflection, we said, how do we deal with this? And it turns out that Ed and I and Dorin happen to be members of an organization called the Association of Space Explorers, which is 90% of all the astronauts and cosmonauts who have flown around the world who have flown. We now have a membership of over 400 astronauts and cosmonauts from about 30-some countries. But in any case, we said, wow, here we are, heroes, okay? We can knock on almost any politician's door, and they're going to listen to us at least one time, okay? So if we want to bring it to the attention of political leaders around the world so that they're ready to make a rational decision, why don't we, the Association of Space Explorers, take on this non-political, this non-technical, but very political challenge? And if the political leaders of the world aren't ready to make a decision when there's a threat, somebody's going to get hit. Dorin happens to be a former Romanian cosmonaut, flew with the Russians a couple times. One of my best friends. It happens when we decided to take this to the world leaders, Dorin was the chairman of the UN Outer Space Committee Technical Subcommittee. Right. Dorin could bring this to the world leaders, right? By the time we took that into the UN and we had it ready to go, but it needed to be approved by the Outer Space Committee, Dorin was chairman of the UN Outer Space Committee. Perfect. So turn it over to Dorin to take in the geopolitical reality.
Thank you very much, Rusty. Thank you very much. Right. Taking into consideration what Rusty said about the asteroid hitting the Earth, try to imagine that the center would be Eastern Europe or Western Europe, and one side it's where? Far East, and the other side it's where? The US maybe. So try to imagine what big political problems are. How to deflect the asteroid. If the deflection is not completed, is not done accurately, so the asteroid always hits the Earth in one or on the other side. Okay, this is my presentation. So what is the most important organization in the world that can take decisions with respect to the most important problems of us? Is the United Nations. So the United Nations comprise now 193 member states. So when a decision is taken at the level of the General Assembly of the United Nations, all these countries, all these member states are obliged to take it into consideration. So we work in the framework of the Association of Space Explorers, starting with 2005. In 2005, we had a congress in the United States, in Utah, and Rusty just proposed to organize a committee on near-Earth objects, and I said, yes, I will be part of that. There were some other friends, Europe, Canada, United States, and so on, and started to work. But in the same time, from since 1992, I started to represent my country at the United Nations Committee on the Peaceful Uses of Outer Space. In 1993, I've seen that there are a lot of observer members, international organizations of this committee. And instantly I called Houston, was Ted Everts in that time, if I remember well, the director of our association. Ted, look what happened in New York. The committee was in New York in that time, from 94 meets in Vienna. And just to ask our leaders of the Association of Space Explorers if they agree to become members, observer members of this committee. In the same fall, Alexei Leonov from one side, Tom Stafford from the other side, Rusty was there, and a lot of other cosmonauts and astronauts met the director of the Office for Outer Space Affairs, and he took part in our Congress in the US, and if I remember well, February next year, our association became an observer member of the UN, having the opportunity to express things, professional things, opinions, to take part in debates, and so on. So we decided, not in 2005, a little bit later, to involve our association with the United Nations. So actually in 1999 took place a big international conference organized by the United Nations, the Unispace 3 conference, the Space Millennium Vienna Declaration on Space and Human Development. It was a resolution of the United Nations, and that was stated that to improve the scientific knowledge of near and outer space by promoting cooperative activities in such areas as astronomy, space biology, and medicine, space physics, the study of near-Earth objects and planetary explorations should be organized groups, working groups, inside of this COPUOS, Committee on the Peaceful Uses of Outer Space. And of course, was about the international cooperation, also studying near-Earth objects, and to implement such mechanisms, there were some recommendations. It was organized a working group on near-Earth objects. Before the working group, after this Unispace 3, was organized an action team, a team of specialists that bring their knowledge and define exactly the problem to be approached by the UN. The action team 14 was the action team on near-Earth objects. It was organized to review the content, structure, and organization of ongoing efforts in the field of near-Earth objects, to identify any gaps in the ongoing work where additional coordination is required and or where other countries or organizations could make contributions, and to propose steps for the improvement of international coordination in collaboration with specialized bodies. So it's a picture with me as a chairman of COPUOS, also with my previous chairman, also Sergio Camacho, who led many years the working group on near-Earth objects within the UN, with the chairman of that time when they started to talk about near-Earth objects. In the framework of the scientific and technical subcommittee of this committee of the United Nations was organized that working group. So the process was organized in this framework of this working group between 2009 and 2011, and also the work was extended till 2012, 2013, when this working group proposed to the committee a lot of measures to be taken. The committee proposed to the General Assembly, and they approved the organization of 2 institutions. These institutions, in the framework of the United Nations, are an International Asteroid Working Network and a Space Mission Planning Advisory Group. So the first one has as an object it's open to contributions by the wide spectrum of organizations, and was established in 2014. And what it does, it looks for the asteroids, determines the orbits, gathers the information from all these very nice guys here and from all institutions that deal with the asteroids, and determine which of these asteroids is dangerous for the Earth, and inform the governments, inform the United Nations. And the second institution, Space Mission Planning Advisory Group, established by the UN, includes big space agencies that could cooperate and take technical measures to deflect the orbit. So all these institutions started to work in, the working group of the Action Team 14, Rusty Schweikart is there, me, some other people involved in these things in 2010 in Mexico City. All these institutions work together with this Committee on the Peaceful Uses of Outer Space and with the employers of the United Nations, organized in the framework of the Office for Outer Space Affairs, which is located in Vienna. So the first institutions determine the impact time, location, severity of the impact. The second one, space mission plans, coordination. And in cases of credible threat, they inform instantly the UN and the member states. So both of these institutions, they report every year in February to the committee itself in Vienna, and they inform by not verbal, they made reports, and they inform about the work of this committee, of these asteroid institutions, let's say. The General Assembly approved the organization of these institutions. A lot of member states are part of them. A lot of specialists are part of them. And when they were organized, the General Assembly welcomes with satisfaction the recommendations for an international response to the near-Earth object impact threat endorsed by the Scientific and Technical Subcommittee, by the session, and so on, and by the committee. So what the Association of Space Explorers did? I didn't put, no. Well, where is the thread? So I just want to show once again the report of the Association of Space Explorers. This report, the asteroid threat, a call for global response, was written by a panel of international specialists gathered by the Association of Space Explorers. Me, Rusty, other friends, we gathered a lot of money, about $100,000, to organize 4 international workshops in different parts of the world, to gather all these specialists and to use their knowledge to write this very well and deep studied report. That report was submitted in 2009 by Rusty Schweikart. You see Rusty here in the picture, informing the United Nations about our report, and this report became a working document of the United Nations and helped a lot in promoting the problems, in promoting the solutions, mainly solutions for solving the problem, solving in a way from UN point of view, solving the problem of near-Earth objects. So, well, in the same time, the Association of Space Explorers was very much involved in promoting the Asteroid Day. So we marked the Asteroid Day here. In 2016, in February, at the session of the Scientific and Technical Subcommittee, me and Tom Jones wrote a report to the United Nations. I presented the report to the committee, actually asking the United Nations to declare the Asteroid Day as a global observance, annual global observance. And the United Nations Assembly in December 2016 declared the 30th of June International Asteroid Day to observe each year at the international level the anniversary of the Tunguska impact over Siberia, Russian Federation, on 30th of June 1908, and to raise public awareness about the asteroid impact hazard. You see the General Assembly of the United Nations, the hall in New York, they declare all these things. And I've got from the Asteroid Day co-founders diploma as the first official ambassador of the Asteroid Days because I did all these things. And next year in 2017, an asteroid got my name. It's in just by hazard, or maybe not by hazard. That asteroid with a diameter of about 6 kilometers since the main belt of the asteroids was discovered in the year when I flew into space in 1981. So it's what we did at the level of the UN and is the way we act to organize at a global level these things with the main goal to save the world in a way. Okay, thank you.
Before we go to Q&A, let me summarize in what I consider plain language what we're dealing with here and the reason why Asteroid Day is so important. I think from the description I gave, Dorin talked more about the process that we underwent given the geopolitical reality of somebody having to make a decision to act and what way to do it, etc. So that's a political issue. And the problem or the challenge with political issues is unless the general public understands or has some understanding of what their politicians ought to do or what they want them to do, politicians will act in their own self-interest. I mean, that's just part of reality. And so the reason why we really started Asteroid Day was so that the general public would gradually come to understand what this challenge is all about. Because if, when we end up with a threat, politicians simply start debating, they'll debate forever until the damn thing hits. So there's got to be a general public understanding that there is a timeliness involved, that the decision makers, their politicians, can't just sit around and debate because you pass a date when it becomes too late to act. And then it's going to hit. Okay, so that's a reality that the politicians would not have faced if we didn't take this action to bring it into the United Nations. Now, many, many people look at the United Nations and say, for Christ's sake, why'd you take it to the United Nations? What a dumb organization to get anything done. Maybe true. But as Dorin said at the beginning, there's only one organization that basically represents everybody on the planet, and that's the United Nations, number one. Number two, and this is something which is hard to appreciate, the United Nations is extremely slow to act and to do anything. And we've been working at this since 2005, basically 2006, thereabouts. And all that exists are those two organizations Dorin mentioned, and they're like skeletons, okay? They're skeleton organizations, but their responsibility is defined, and basically the General Assembly sent the whole thing back to the Outer Space Committee, COPUOS, but Outer Space Committee, and said, put muscle on that skeleton. Let's get real capability in those organizations. So we, after almost 10 years, we've got the skeleton, but it's pretty bare. But over time, it will get muscle on it. And one of the things you realize about the United Nations is that while it's extremely slow to make a decision, when it makes a decision, it's hell trying to stop it. Really. I mean, the world has made a decision. And one of the things you realize when you get into this challenge of planetary defense is that when we deflect an asteroid, we is the planet, not the United States, not Romania, not EU. The planet will end up having made a decision to deflect another cosmic object. Deflect, change its orbit a little bit, reshape the solar system in order to enhance survival of life on this planet. That's what it's all about. And that's why we had to take it to the United Nations and why we're very proud to be here today and each year with Asteroid Day to bring the public into this geopolitical decision, which ultimately, at some point, will have to be made. So let's have questions for Dorin, and then we'll break at the end of that so that these guys can get to a press conference.
Please.
You talked before about deflection, about moving that point along a line, a specific line, in case this sort of thing happened. So my question is, okay, tomorrow an asteroid is falling. Where do we move it? How do we decide?
Yeah. Okay. Let me
Tomorrow,
try
nowhere.
Yeah. This is a question on deflection. So let me try to give a simple explanation for deflection. There's a lot of detail, but at the simple level, what you're doing in order to accomplish an asteroid deflection is to change its arrival time 10 years in the future. You have to predict well ahead of time because it takes time to get things done. But if 10 years from now it's going to hit the Earth, or you believe that it's going to hit the Earth, what you do with a deflection is change its arrival time very slightly. It takes, you have a three-dimensional intersection that the Earth and the asteroid are both going through at the same time, okay? And it takes the Earth 8 minutes from the time the leading edge of the Earth gets to that intersection until the trailing edge of the Earth leaves that intersection. So there's 8 minutes, 10 years from now, when the asteroid could hit the Earth. So if it's going to hit in the middle, all you got to do is change the arrival time of the asteroid so that if you make it arrive late 4 minutes, the Earth will have gotten through the intersection. Or if you make the asteroid arrive early, then it will have gotten through the intersection before the Earth gets there. And that's what a deflection is all about, just changing the arrival time, say 4, 6, 8 minutes, and you got to start that about 10 years ahead of time. And the way you do that is you change its speed just a very little bit way ahead of time. How do you change its speed? Run into the sucker. That's the easy way, right? There are different ways you can do it, but basically you're going to change, one way or another, you're going to change its orbital speed just a little bit, a thousandth of a mile an hour, for example, that kind of level, and 10 years later, it arrives 6 minutes late for the crash. Doesn't happen. Okay, that's what it's all about.
So I understand that you can't take measures now for tomorrow. You have to send a rocket or something to the asteroid years before he hits the Earth. He could hit the Earth.
But happily, things behave almost Newtonian, and you can predict. If you have enough observations, you can predict that far ahead of time that there will be one and take action. If you can get somebody to make a decision, that's the issue. Yes, sir.
Rusty, may I ask something totally inappropriate?
At last, yes.
Recently, your president has announced the 6th branch of the military, the Space Force. I was wondering, what kind of ideas are behind it? And secondly, do we now all need a Bruce Willis at our side?
I could answer that bit of that too.
Well, Ed will have a comment too, but let me just say that number one, there are basically two reports that have come out within the last week, really. One relates directly to what we're talking about, near-Earth objects and planetary defense, but that is not the one you refer to. The other one is the one you refer to, which is the creation of a quote-unquote space force, the equivalent of the Air Force or the Navy or the Marines or the Coast Guard, et cetera. That is a purely internal military issue. They're dealing with national defense. This is an issue which has nothing to do with the work that we do, which is purely open and civilian. Now, is there an intersection between the two? Potentially. But let me just say that one of the realizations, in particular when you look at the geopolitical issues and you think about what I said a moment ago, that essentially the world has to decide to deflect an asteroid. there has to be, if you could just picture that really happening, I mean, really face that in your mind, and you realize there must be a great deal of public trust in the mechanization of that decision. Okay, you've got to have the public trust. The worst thing you could do would be for generating and containing public or eliciting public trust is to say, don't worry about it, the U.S. Space Force is going to take care of it, right? President Trump and the U.S. Space Force is going to take care of it. Don't worry. Right. So that the one thing that we realized as we worked in the United Nations that you really don't want to have is the military with all of secrecy, necessity of secrecy, and all of that directly involved. This should be, as all of us have been involved in the past, a civilian operation. It is everything that Ed and everybody else has been talking about here, that Alan has been talking about, is on the web every night, thousands of observations. It's all there for everybody to see wide open. As soon as you get into beginning to involve military, you can kiss the general world population trust goodbye. I mean, it's just
and in fact, as Rusty said, that proposal had nothing to do with asteroids. It was, as Rusty said, purely an administrative thing regarding whose budget is controlled by who. So much of the reporting, I have to say, about the proposal for the Space Force has been wildly badly done by poorly informed reporters who didn't take 5 minutes to do a Google search and see what it was about. They simply wrote articles which were, I mean, extremely poorly done. So I would say, as with most things, do your own research. I mean, don't trust what you read. But Rusty's point about the keeping the process open is extremely important, because the data needs to be available. The analysis and the understanding of the analysis tools needs to be open for people to verify the calculations. And that's an important part of this whole thing. And in fact, you can't just say, well, this is the orbit. You have to say, here are the uncertainties in the orbit, because that affects the probability that we understand that something is going to hit. And so that aspect of things is something we're all striving to do, and that is why it's important to have these things be open.
Yes, go ahead.
I'm Edgar from SES. So the presentation, I think, was particularly interesting in depicting how long it took to have, as you called, Rusty, the bare bones of something that at a geopolitical level could work, right? Yes. And I find it illuminating, let's say, on the capability of getting somewhere, and extremely scary, because I suppose that the bare bone is not enough, and then there must be muscles on top of that. And I'm, let's say, after the presentation, I'm not too confident that if the thing is coming to hit, and somebody can start raising a yellow flag, then there will be an immediate reaction. I still see that there will be a huge geopolitical debate. We also don't have, as you were stressing before, today the observational means to detect things in advance, to characterize things in advance. So I think it has also a subtle line of fear, right?
At a certain time, we had to start to organize all these things. They could be started in 20 years from now or 20 years before, but we didn't have enough information till now. Now, when we have a rate of discovery of the asteroids pretty high, not as much as we wish to, but pretty high, we really acknowledge that we need such institutions. They started to be organized. It will take maybe another 10 years, 15 years, when they could aggregate real decision, but they started to work. This is very important.
Let me paint reality from my point of view. And I'm no longer directly involved in any of this work. I'm emeritus. I'm a has-been, okay? But I will speak truth. my truth, right? My truth in this, and I want to pick up on what Dorin said. You're never going to get there with a timely decision out of the geopolitical world if you don't start. So we started when it was rationally possible, logically possible, to start introducing this to the geopolitical world. Yes, indeed, it's going to take a long time to get muscle on those bones. And even after you get muscle on the bones, when a real impact threat emerges, you're exactly right. There's going to be people are going to wave flag and say, we don't care what we agreed to back then. You know, it's coming over our country. We're going to have we want it to go the other way or whatever. We're not going to pay for it or, all kinds of things. So my political reality is we're going to get hit because the politicians are going to debate. Happily, the probability that we get hit with a really big one is near zero. The first one that's going to hit is going to be a relatively small one. And so maybe a few people are endangered, and happily we can usually evacuate for relatively small ones. More than likely, the first one that's predicted to hit and does hit will hit in the ocean. So there will be, it seems to me, an impact where the politicians have screwed up and not taken action. Okay? But the next time, and the next time, and the next time, etc. So you have to start.
And Rusty and I disagree on this. I actually think
this is
that
my political.
yeah,
he's got different truth.
I actually think that the first time we do find something that has a very high probability of hitting the Earth, then in fact the physics will say one way of deflecting it is much easier than another way. Especially for kinetic impactors, it's almost always the case. Then that we will actually move it. And I think that's going to be a pivotal moment in human history, the first time that, as Rusty said, that human beings have engineered the solar system in some way to change what would have been something which was, a cosmic collision, actually preventing that. And I think we'll actually do it. And part of the reason I think we'll be able to do it is because if you look at the advances in space technology right now, this is going to get to the point where it isn't, a multi-billion-dollar program. It isn't a deflection of an asteroid. Might actually be something within the capabilities of, let's say a particular city is in the target. They could say, hey, look, we're going to raise a few $100 million and we're going to deflect this asteroid, because if that city is actually in danger, they can actually fund it. The civic leaders of nearly any city could easily raise the amount of money. I mean, we're literally talking probably, a few $100 million at most. And if you think about the typical scale of construction projects within any particular city, that's doable. So I think there will be a deflection.
Mark talked about being out of the box, or maybe we talked about him being out of the box, but I'll give you a real out of the box here, picking up on Ed. My own thinking has been that it is people like Elon Musk and Jeff Bezos who may make that first deflection really possible, because as Ed said, once you have an impact threat, you can see the line of risk, what we call the risk corridor, across the Earth. That asteroid isn't going to hit anywhere else other than on that line somewhere if it's going to hit. So you can see, as time goes on, the property values along that line plummeting unless there is a threat, there is a possibility of deflecting it. So anybody with an investment along that line is going to put in 1/10 the value of their property, or whatever, however it might decrease, in order to fund and pay not a government, but a private enterprise company to launch and deflect it. So perhaps, in spite of what we've done, one of the most likely salvations here for eliminating an impact, is to privately contract for a deflection. And I dare say even the governments of the world would have a very hard time stopping a private enterprise from deflecting an asteroid and protecting life on Earth. That would be a pretty tough thing to say, no, you can't launch from our launch facility or whatever. So, I mean, there are a lot of complexities on this, but we have started both the technical work to be able to discover these asteroids and predict future impacts, and we've begun the work in the United Nations and with Asteroid Day to say that there should be a geopolitical response ready and the education in the world population to actually put pressure on, or the other side of the coin, to support their politicians in making a rational decision. Yeah.
Are you aware of some, let's say, opponents who are questioning your approach, what we already experienced in the climate change problem, in which there's a consensus within the scientific community that, yes, climate change is there. There are still people arguing against. And are you also facing this kind of, let's say, threat that somebody else in the community says, okay, everything you're talking about is simply a joke, we don't believe it, don't do anything?
Let me just say, every one of us probably has 5 answers to the climate analog, okay, the climate change analog. But let me just give one, and then I'm going to turn it over to Mark, who is a specialist not only with asteroids but in climate change. My comment is that when you're talking about global warming or climate change and you want to do something about it, basically everybody in the world has to change their behavior. When you want to stop an asteroid, almost nobody in the world has to do a damn thing in terms of changing their behavior. It's an easier problem.
I guess I would say one of the analogies, I mentioned geoengineering in my talk, and the idea of behind geoengineering, there's multiple ways to do that. One is to extract CO2 from the atmosphere and return it to more natural values and the radiative balance into more natural values. Another way, which I do not advocate, but I fear will become necessary out of desperation, is solar energy management, basically somehow shading the Earth, either by putting sulfate aerosols into the atmosphere or by busting up an asteroid to make dust to reflect sunlight from around L1, something like that. But if you do one of those things, it's not a zero-sum game. There will be winners and losers. And so very much as Rusty pointed out with this impact corridor, if you push it one way, you're increasing the risk on one continent, and if you push it the other way, you're increasing, maybe hopefully temporarily, the risk on another continent, and that's going to reduce economic development, it's going to reduce property values, it's going to do everything. So you can imagine, pushing it east, if it's going to hit in the Pacific, pushing it eastward across California or westward across China, it is going to hurt the economy of one nation or the other. And so it's very, in my mind, it's very similar. The analogy is very strong.
I think, though, as far as questioning the realness of this, do asteroid impacts happen, and are they really bad? Can they be really bad if a big one hits? I have never heard anyone credible question that. So I think it's quite a bit different in that sense.
And the science, the basic science itself is far more settled in something
it's a lot
like
easier. Object A hits object B. Okay, it's much simpler. So I think Rusty's correct. It's also in terms of the well, no. Well, but climate is a different thing. Climate is a very different thing. But the reticence of folks to want to do things for, as Rusty said, for issues that affect the world economy, and they really do, for energy and climate issues, that really does affect everybody's lifestyle, if you'd like, and trillions of dollars of money, okay? Whereas, as I said, you know, the solution to a typical asteroid impact is measured in, you know, amounts of money that are equivalent to building a building, or a street, or a football stadium, probably less than a football stadium. So, you know, it's a very different thing.
If I can just say one last thing going on from that, I think when I spoke to people, they haven't questioned it. I think the biggest separation between reality and perception that I face is that they've always assumed that we can immediately do something about it. And I think this is something that Asteroid Day itself, as an event, is trying to push over that. Actually finding these things is difficult. Figuring out if they're going to hit can be more difficult. Preventing that impact through the deflection is something we've never even tried yet. And so I think there needs to be more perception on that level to actually get that message over, rather than just the fundamental outlines of an asteroid hitting you, making it a bad day for everyone.
Yeah, let me pick up on that because Alan makes a very good point. When we started Asteroid Day back basically 4 to 5 years ago, as I said in introducing Ed, we realized that nothing at all can be done if you don't know that asteroid that's going to hit you is out there, and what its orbit is, et cetera, et cetera. So the most important thing is to find them. And we realized that, frankly, the Congress in the United States or any legislative body, anybody who's going to allocate money, by and large, they don't have a clue why they should do that in terms of asteroids. And so one of the things that we made an essential part of Asteroid Day was encouraging people to sign up to what we call the 100X Declaration. And Mark and I and others here wrote and edited that declaration, which basically says we, the public, want you, the politicians and legislators and whatnot, to provide the money to the space agencies and others to, you know, build better telescopes to get on with this discovery rate. Because at the rate at which, at that time, we were discovering asteroids, and even today, by the time you get knowledge of, let's say, 90% of the asteroids that can actually kill people on the ground if they hit, it would be 1,000 years from now. So the thing that we pushed right at the outset was signing the 100X Declaration. And for any of you out there who have not gone online on asteroidday.org to sign the declaration, do it. We need hundreds of thousands, millions of signatures that say, spend that money to find them, because that's, you know, step number uno right there. Okay, so now we're basically running out of time here. Excuse me. The press conference is going to start in about 20 minutes. So, Danica, I'm going to turn it back to you. If you want to turn over for more questions, please do. And Dorin and I, in any event, will be here while these guys go to a press conference, so you can beat on Dorin and I, and we'll answer their questions. It will give you the real truth. Let them go talk to the press.
Yes, so thank you. I just wanted to let you all know that there is a reception. It'll be next door. I'm going to whisk a few of these folks away. Max Alexander, our photographer, is right here. If some of you would like some nice photos, we'll work on making some of those available as long as you identify yourself to George and Max so we know who to send the photos to when they are processed in the next couple of days. And I've left on some of the table, some of the chairs, there's our annual report for B612. If they're of interest, all the photos were taken while Ed was on the International Space Station. I think do we have some other information we wanted to pass out or share, George? No, okay, great. So I just really would like to say thank you. Could you click the thing forward, the screen, please? I just want to say thank you to all the sponsors again. This day really was made possible by FNR and a partnership with SNT and ART for providing this beautiful facility, and Asteroid Day Live and our year-round program is really supported quite significantly by the Luxembourg community. And so this team being able to be here to talk to you about asteroids and asteroid science is really at the courtesy of all of these great supporters. Thank you, SES. I've got 2 people from SES. Thank you. I don't know if I have any BCE people here. So I hope you enjoyed the conversation. You can continue it with Rusty and Dorin next door, and I hope we see you next year or at some of our other activities over the course of the year for the Asteroid Foundation. So thank you. And I'll take my meteorite.
Your asteroid, Danica.
No, it came through the atmosphere.